Lebesgue's approach was very similar to Riemann's approach. Riemann had taken a partition of the domain into finitely many parts, and Lebesgue took a partition of the codomain. So I take some partition, this point, this point, this point. Suppose I take these things. Maybe I will take, let me just take these points. So I have first subinterval, second, third and fourth. Then he would again construct a set of rectangles below and above in the following way. Let's clearly understand how he is doing it. I will just draw horizontal lines through each of these partition points. Now consider these as rivers. River 1, river 2, like this. Now you will try to construct the lower approximation in the following way. First start with this river. In this river, no part of the curve is intersecting this river, so just leave it blank. Come to the next river. Here you see this is part of the curve and here is another part of the curve which is in this river. So what you do is you just draw a vertical line to align yourself and then take this part and bring it flat down to the floor. So it is like a cell and part of the curve is inside the cell. Take this curve and flatten it on the floor of the cell. So you are approximating this fellow by this. Now here in this cell there is no part of the curve, ignore it. In this cell you have part of the curve. So take this, flatten it down on the floor. So you get this. Here no part of the curve, so leave it as it is. So I have got two things with the same height. Now come to this river. Here again just extend this and extend this. So look at all the parts of the curve that are inside this river. Here you have its cell, flatten it down on the floor. In this cell there is no part of the curve, leave it. Here you have this part, flatten it down on the floor, no part of the curve. Now you come here, only one part is there, so this is the cell where this part lies. Flatten it down on the floor. So you get this, you have finished all the rivers. You have approximated the curve using this function. So the function takes this value over this interval, this over this interval, like this. In this particular example, it turns out to be a nice step function. It need not always be a step function, as we are going to see. So again, Lebesgue would say, I would try to approximate this area by the total area of all these rectangles that he has created. His rectangles are like this. Rectangles 1, 2, 3, 4, 5. Okay, now he has to do a similar thing to approximate it from above. Very similar to what we did just now, except that now we will flatten every part against its ceiling. So in this case, I shall take this and flatten it against its ceiling, which means I will take this line. Flatten it against its ceiling, so I will take this line. Against its ceiling, that is this line. This part will be flattened against its ceiling and this part against its ceiling. So you get another set of rectangles. This time these are above the curve. And then Lebesgue made the same thing as Riemann had done. He said that if this set of rectangles and those set of rectangles, you take all arbitrary partitions, of course finitely many parts. If you find that the supremum of all these things equals the infimum of all those things, then you will say that this function is integrable and that common value will be called the area under the curve, just as Riemann had done. Let's quickly write it down in language of mathematics. For Riemann's case, we had this language called step function, but here This particular example looks like a step function, but in general it need not be, so we need a new terminology. We shall use the term simple function to denote a function that takes only finitely many values. For example, this lower approximation is actually a simple function because it takes this value, and this value. Similarly, the upper approximation is also another simple function which takes this value, and this value. Only finitely many. The same value may be taken at lots of different places, but it is not taking infinitely many values. So, as in case of Riemann, we define script S is the set of all simple functions on AB. Earlier we had script D, set of all step functions with finitely many steps. Now I will write that standard inf sup argument. When I approximate it with below, I do it like this: S is less than or equal to F, S is a simple function, and I am computing its area. Well, area, as in this example, again it's just a bunch of rectangles, so length of the base times the height. And I do it again from above, where I work with inf rather than sup, and this inequality has reversed. Other than that, it is same. So, if these two things happen to be equal, I shall say that the area under the curve is equal to that common value, and that is something again we shall define by f over the set A to B, and that is what we shall term the Lebesgue integral. Now you might be wondering from the description, so what is the big deal? Riemann did it in this way, Lebesgue did it in that way. Of course, the same criticism can be leveled against this fellow also. Is it true that it is always equal? No, unfortunately no. Again, as before, it is in general less than or equal to. In some cases, equality may not prevail, in which case we will say it is not Lebesgue integrable, and we cannot talk about this integral in those cases. So what's the great advantage of thinking in terms of Lebesgue as opposed to in terms of Riemann's approach? That's what we shall take up in the next video. In this exercise, we want to do what we did for Riemann's integral in the last exercise. I have given you a function bounded from above by capital M, non-negative, and it has a discontinuity, a removable discontinuity. This point has been shifted down here, and I have given you one partition of the codomain. Your job is to obtain by actual sketching the lower approximation and the upper approximation in the Lebesgue sense.